we're examining the heights of female grad students. And we take a very large population of female grad students, and we say to ourselves that that female grad students, the average height of female grad students is 65 inches. And the standard deviation for the average height is 3 inches. You guys remember how we calculated the standard deviation? It was just a difference of all. It gives us an idea of the spread, right? The difference we took the difference between the mean and each individual value. We squared it. Some are squares. We divided by n, and we got the variance and the squared standard deviation. But it's a number that we calculated. I warned you it was going to be a pretty useful number before. So now we're going to see why it's a useful number. Okay, the idea here is that where are most of these? If I were to ask you what's the most common height, I'm just breaking these up into inches. Let's say I didn't bother to measure tenths of inches. I just rounded it to the total number of inches. What's the most likely outcome if I were randomly going to pick people out of this population? Well, it's going to be the mean, right? The most likely outcome. The most people are going to be 65 inches tall. Right? What about 64 inches? Well, if it's really a normal distribution, it's just as likely that people will be shorter than the mean as they are taller than the mean. It'll be symmetrical, right? So my next most likely outcome would be 64 or 66. And the next most likely outcome after that is going to be 63 or 67. Okay, and the next most likely outcome after that is going to be 68 or 62 and 61 and 69 and so on and so forth, right? So what's happening here? We're creating a distribution that is symmetrical around the mean, but the mean is the most likely outcome. So this is what we would call a normal distribution. And what's the characteristic of this? The characteristic of this is that if I pick an individual out at random in the population, the only thing that determines whether they're greater than or less than the mean is pure chance, right? Nothing else determines it, just chance. Because half of them are more, half of them are less. It's like reaching into a bag with 12 red balls and 12 blue balls, pulling one out. Just pure chance that determines which one I'm going to get, when I'm going to pick, right? So, but as I get further and further away from the mean, we have fewer and fewer people that are that height. So the probability of my getting someone that's 61 inches or 60 inches tall is much less than somebody that's 66 inches tall, or certainly the mean 65 inches. Okay, so this is what we would call a normal distribution. And it takes the shape of a bell curve. Now, if instead I measured everybody to the 100th of an inch, we might get things where these little histogram bars are so close together that they almost form a line, a continuous line, a bell curve like that. Okay, so let's assume for a moment that that's indeed what they form. Okay, remember I just told you quickly that, you know, if the mean is 65 and the standard deviation is 3, well, gee, almost all the values are going to be between 3 standard deviations below the mean, which is 9 inches, which would be 56 inches, and 3 standard deviations above the mean, which would be 74 inches. That would represent almost all of the population. You might have somebody a little taller or a little shorter, right? But that'd be a pretty uncommon outcome, right? So 99.7% of the population is probably going to be within that range. Came up with that number for a reason. Okay, so let's take a look. Let's take that one step further. Oops. Okay. Don't bail out on me here. Okay. We're going to take it one step further, and we're going to relate that to all standard deviations, all normal distributions that are based on chance. So let's see. Okay, so normal distribution is going to be something where the selection is a numerical variable, and the selection criteria is going to be based purely on chance. So I could have a situation where the mean is, say, let's say mean is 50. I'm going to take a population. I could have a situation where the standard deviation for that mean is 2. Okay, what would that look like? that might look something like this. Right? The mean is 50. This is symmetrical, and the standard deviation is 2. Right? So 1 standard deviation, 2 standard. So the values are somewhere between 44 and 56, almost all of that population. I could also have a population where the mean is equal to 50, but the standard deviation is equal to 10. What does that look like? Well, if I put the same scale here, that's going to look more something like this. Right? Still symmetrical, right? But the values, if this is 50, 3 standard deviation goes 20 to 80. It's flatter, right? However, all of these normal distributions have some common properties. And that is that number one, they're symmetrical. Number two, the mean represents half of the values. Half of the values below the mean, half of the values above the mean. You know, before we were talking about situations where the median was different than the mean, right? That's not really a normal distribution anymore, is it? Because it's not symmetrical, right? So all of the work we're doing here is based on the fact that we're assuming that we're working with a normal distribution, right? A perfect normal distribution. We're willing to tolerate, especially as we move on, we're willing to tolerate some drift away from a perfect normal distribution, but it's really most of the work is based on that idea. Okay, so now what do these things have in common? What they have in common is that even though they're spread out like this, they have in common the fact that the areas underneath these distributions represent portions of the population or probabilities. I can look at it 2 ways. Everything under here represents 100% of that population, all the people in that population, or I could look at it as this represents the probability of randomly picking everybody in that population. So what's the probability of my picking someone that's less than 50 in this population, in either one of them? 50%. More than.
Is that really true though?
Yeah.
Like 50% is the mode also, right? So you have to take into account, isn't it like equals the odds of picking 50 or less?
Yeah, you could phrase it that way. Yeah. Yeah, maybe you wouldn't include 50. Okay. 50 or less, or less than 50. I'm not sure if you'd include it anyway. Right. Actually, to tell you the truth, it's interesting that you brought that up, because if you just pick out a single, with a numerical variable, if you just pick out a single value, like if I picked out the value 50.195, right? That's a straight line, right? So the area that's represented by that is the height times the width. Straight line has no width. So basically any value has no area. So you could really phrase it either way.
It's like a continuous numerical variable.
Right. Yeah. Yeah. So at any rate, and that's what we're talking about is continuous numerical variables. Okay, so now what about if I'm 1 standard deviation below the mean, right? Which in this case would be 40, right? In this case, 1 standard deviation below the mean would be how much? 48. The area between 40 and 50 is the same, percentage-wise, is the same as the area between 48 and 50. Right? They have common properties based on the standard deviation. Okay, so we're going to apply that. Okay, in fact, first, before we apply that, believe it or not, there is a formula that you can use to calculate these. I don't think I showed you the formula yet in this part, but we'll get to it in a second. Okay. Before we get to the formula, I'm going to give you some general rules of thumb that you can use. And these are termed the empirical rule. Okay, Levi kind of broached this before. And basically, for a normal distribution, not standard, but for any normal distribution, true normal distribution, well, let's see, 68% of the values, probabilities, or people, or values, are going to be between 1 standard deviation below the mean and 1 standard deviation above the mean. 95% of the values are going to be between 2 standard deviations below and 2 standard deviations above. Okay, and 99.7% is going to be between 3 standard deviations below and 3 standard deviations above. Doesn't matter if the distribution looks like this. Oops, let's go back a page. Looks like this tall, narrow one, or the short, flat one, right? Because We're talking not about actual values, but standard deviations for that distribution. Okay, so we're going to apply that. There's another document that's on Blackboard that's listed with a B, right, which is going to be examples using the empirical rule. Okay, I'm going to try one first, and you got an extra version of it there for you to look at. Okay, let's blow it up a little bit so we can see it. Okay, assume that the heights of adult Caucasian men have a mean of 68 inches and a standard deviation of 4 inches, and they're normally distributed. Find the probability that a randomly chosen individual from this population has a height greater than 68 inches. That's an easy one. 50%. Between 64 and 72 inches. What's the standard deviation? 4 inches. So 64 is how many standard deviations below the mean? Remember, standard deviation is 4, so it's 1 standard deviation below the mean. Right, so between here and here is going to be 68% of the population. Well, the probability is going to be 68%. How about between 60 and 76? How many standard deviations below is 60? 2 standard deviations. How many above? 2. What did we say was the the area under the curve for 2 below and 2 above standard deviation? 95%. Right? Okay, good. I'm going to go to the next one. Okay, assume the heights of adult Caucasian women have a mean of 63 and a standard deviation of 3 inches. What percentage of the women in this population, again, greater than 63 inches? 50%. Bingo. Greater than 66 inches. Uh-oh, a little bit of a twist there, right? I'm going to pull up this piece of paper, and I'm going to actually sketch this normal distribution. Okay, and we're working with some pretty simple examples of this so far, but it can get a little bit hairy once you start working on this a bit more. I got to get this one out of the way. So I got somewhere to write, and I can see what this one behind us has. Let me move this over a little bit so we can see both at the same time. Okay, so we want to know what's the area. So let's draw this distribution. Here we are. The mean is equal to 63, right? So greater than 63 inches is going to be this area here. Greater than 66 inches. What was the standard deviation? 3 inches. 3. Okay, so 63 inches. Oops. 63. So 66 inches, right? Area greater than 66 is going to be this area in here, right? Well, let's see what that might be. How many standard deviations above the mean is that? 1, right? How many standard deviations below the mean would be its sister on the other side? In other words, minus 1 standard deviation, right? That would be the value 60, right? Don't care so much about the value 60, but I know this area is how much? Between 1 standard deviation above and 1 below. Okay, I'm going to call it 68%, right? 68%. So what does that mean? Since it's symmetrical, how much of that is to the right of the mean and to the left of the mean? 34% and 34%. How much of this population is above the mean? 50%, right? Right? 50% is above the mean. So what does that leave for the darkened area here if this is 34% and the whole right side here is 50%? Right, 16%. So 16%, I'm rounding these numbers drastically so I don't have to play around with this too much. 16% of the population is likely to be above that level, right? And if I were to pick one random person out of the population, the chances that that person would be greater than 66 inches, the height is greater than 66 inches, is 16%. So what was the third question? Less than 60 inches. Okay, less than 60 inches. That's this area down here. Well, what can you tell me about this area and the one we just calculated? They're the same because symmetrical, right? Or you could use the same logic again and say this is 34, so that only leaves 16 for that. Or you could just say it's symmetrical. Okay, so you see the power of this now? By knowing the mean and the standard deviation, if the population is truly normally distributed, we have all sorts of information about it. Okay, so let's go move on. Okay, I'm going to give you guys, tell you what, once you do number 5, you guys do number 5, you guys online do number 5 on your own for a second. Okay, and I'll give you about 2 or 3 minutes to get ahead of me. Okay, and I would suggest that you draw the distribution. I'm going to do that part with you right now. Okay, draw the distribution. It's going to help you from winding up with errors. Let's just slow it down here.